Bismillahirrahmanirrahim. Assalamualaikum and hello everyone. My name is Saidatul Syahira binti Saidi and I am currently a student of Financial Mathematics in University Science Islam Malaysia. In this video presentation, I will be discussing the application of differential equation and their solution using Mathematica. We are focused on real-world example, which is Newton's law of cooling. So, we will see how this classic physics principle can be modeled mathematically, solved using Mathematica, and visualized to better understand how things go down. So, let's begin.
Now, we will moving to introduction of this presentation. Differential equations are important in science and engineering because they help describe how quantity change over time. One practical application is Newton's law of cooling, which describes how a hot object cools in a surrounding environment. In this presentation, I will demonstrate how Mathematica can be used to solve this differential equation and analyze the cooling process of an object over time. Next, problem statement. The problem we are solving is how can we predict the temperature of a hot object, for example, a cup of coffee, as it cools down in a room at 27 degrees Celsius. According to Newton's law of cooling, the rate at which an object cools is proportional to the temperature difference between the object and the surrounding air. So, the equation is written as dT over dt equal to negative K minus Ts, where T is temperature of an object, Ts is 27 degrees Celsius, which is surrounding temperature, and K equal to 0.1, the cooling constant. So, this law was proposed by Sir Isaac Newton in 18th century and laid the foundation for modern thermodynamics and heat transfer theory. Then, in order to solve this problem, we follow 5 main steps, which is, the first one is model definition. We express the problem as a first order differential equation. The second one is symbolic solution. We use the solve function in the Mathematica to obtain an exact formula for temperature over time. The third one is numerical simulation. Using this solve, we input values like initial temperature and ambient temperature to simulate real-time cooling. Next, visualization. We use plot to graph the solution and observe how the temperature changes over time. Lastly, interpretation. We analyze how the object cools down and stabilizes. Next, we will move on to computational solution using Mathematica. Now, let's open up the Wolfram Cloud by going to this link. Once logged in, click on Plus New Notebook. Now let's solve the differential equation using Mathematica. Type this following code into the notebook. Now Mathematica gives us the general solution. So right now we simplify the solution to make it more easier to interpret. We are going to define variable for the cooling constant K and environmental temperature so the model become more flexible. Here, we have set K equal to 0.07 and T equal to 25 degrees Celsius. Then, we will plot the temperature over the time for the first 60 minutes to visualize how the object cools. And lastly, Mathematica have given us the graph. Discussion. The graph confirms the temperature decreases exponentially. At the beginning, when the object is much hotter than the room, it cools quickly. Over time, as the temperature gap gets smaller, the cooling slows down and the temperature stabilizes near 27 degrees Celsius. So, by using Mathematica, it helps us to solve the equation analytically, simulate real-world behavior, and visualize results clearly.
In conclusion, Newton's law of cooling gives us a simple yet powerful way to model how objects lose heat to their surrounding over time. By using Mathematica, we were able to solve the equation both symbolically and numerically and visualize how the temperature changes with time. This project has shown how differential equations help us understand real-life processes such as from cooling drinks to forensic. Thank you for watching.